Hello, welcome to the class on A540 Advanced Electromagnetic Theory and Antennas. I'm Professor Rakesh Singh Chatterjee. So in the last class we discussed about the cylindrical waves and we tried to find the fields for TZ and TMZ waves. So now in the wave equation we have considered only for EZ and IZ fields, but then electric field has three components and cylindrical coordinates E rho, E phi and EZ. But we know only Ez from the wave equation for the TMZ case, and we know only Iz from the wave equation for TZ case. So, but we also want to know the fields completely. We want to know E rho, E phi, H rho, H phi also. So how do we get this once we have Ez and Iz? That's what I'm going to discuss now. So now, if you assume that wave is propagating along the z-axis, in that case, we can separate the fields into two components. One component which is called longitudinal components, and those fields are the fields which are along the direction of propagation of the waves. And since the wave is propagating along the z-axis, longitudinal components in this case would be Ez and Iz. And we have solved the wave equation for Ez and Iz. So now what we want is to find the transversal components, which is perpendicular to the direction of the wave propagation. E rho, E phi, H rho and H phi. How do we get it? So now what we do is we solve the wave equation for only Ez and Hz, depending on whether we want TZ waves or TMZ waves. Once we have that, we also want to find the transversal components of the wave. E rho, E phi, H rho and H phi. So now how do we get that? That's what we're going to discuss. How to obtain transversal fringes from the longitudinal fields. Obviously, we can derive this kind of relation from the Maxwell equations. The relation between longitudinal fields and transversal fields can be derived from the Maxwell equations, but derivation will not be discussing. If you are interested, we can always discuss in the online class. So now, to obtain the transversal fringe from the longitudinal fields, we will follow three steps. First step, we define the cutoff Watt number, Kc square is equal to beta square minus beta z square. What was beta square? Beta square was omega square mu epsilon. Beta z is the phase constant along the z direction. This is the cutoff Watt number. We define this first. Then second, we define four functions. Function 1, function 2, function 3 and function 4. And we'll observe that function 1 and function 3 are dependent on Ez components of the field, whereas F2 and F4, function 2 and function 4 are dependent on the Ez component of the fields. So this is the relation. F1 is J beta Z Ez, F2 is J omega mu Hz, F3 is J omega epsilon Ez, F4 is J beta Z Ez. So F1 and F4 I just multiply by J beta Z to Ez and Iz. F2 I multiply by J omega with mu Iz. F3 I multiply by J omega with epsilon Ez. So I know what is function F1, F2 and F4, F3 and F4. I can write down the relations of transversal fields with this function F1, F2, F3 and F4. So now, what is the relation between the transversal fields with the four functions we have just defined in the previous slide? We can definitely find E rho from the F1 and F2 by taking partial derivative with respect to rho of F1, partial derivative of phi with respect to F2. We can find E phi from the F1 and F2 by taking partial derivative with respect to phi and partial derivative with respect to rho of F2. Partial derivative with respect to phi for F1 and partial derivative with respect to rho of F2. Similarly, we can also find H rho from F3 and F4 by taking partial derivative with respect to phi and with respect to rho. We can find H5 from F3 and F4 by taking partial derivative with respect to rho and phi. So now this formula has some kind of simple way of remembering it. So let us look at this formula closely. Outside the bracket, as outside the second bracket, we have 1 by kc square. We have already defined what is kc square, cut off width number. And you can also observe that whenever I do partial derivative with respect to phi, I multiply by 1 by rho. 1 by rho, del by del phi is everywhere. Whenever I do partial derivative with respect to phi, I multiply by 1 by rho. And in order to find E rho and E phi, I do partial derivative with respect to function 1 and function 2. In order to find H rho and H phi, I do partial derivative with respect to F3 and F4. And you can also look at the sign. You have minus minus, minus plus, plus minus, minus minus. These are the sign. And one more observation you can do here is that whenever I want to find E rho, I first do partial derivative of rho with respect to F1, then partial derivative of phi with respect to F2. And whenever I want to find E phi, I do partial derivative with respect to phi of F1 and I do partial derivative with respect to rho of F2. Similarly, I can also find H rho and H phi. So now, when I want to find spherical waves will have TER and we'll consider TMR and TER spherical waves. Waves which are propagating along the radial direction, and in the TER case, electric field will not have any component along the radial direction. In TMR case, magnetic field will not have any component along the radial direction. In order to understand such kind of wave, TER and TM waves, we need to define another vector potential which is called electric vector potential. We have already discussed about the magnetic vector potential. There is something else, another vector potential which is called electric vector potential. As you know that magnetic vector potential was denoted by A vector, electric vector potential is denoted by F vector. So now, once I have this electric vector potential, how do I find the electric field from it? As we have already discussed before, also finding the fields from the vector potential is easier. Similarly, here also, if I want to find fields from the vector potential F, it's easier for me instead of finding the electric field and magnetic field directly. So now, once I have the electric vector potential, how do I find the electric field? That's what we're going to discuss. Consider a source-free region. There are no charges in the source-free region. Then from the Gauss law for electric field, divergence of D should be equal to 0 because this is a source-free region. There are no charges. And we also know that from vector analysis, divergence of curl of a vector is always equal to 0. So now when we compare these two equations, I can equate D is equal to minus curl of F. So you know the relation between electric field and D. D is equal to epsilon E. If I want to find electric field E, then it should be D by epsilon. In that case, if I want to find electric field due to the vector F is minus 1 by epsilon curl of F. So this is the process. This is the process for finding the electric field due to vector F. So when vector F is known to us, how do I find the electric field? That was the question we were discussing in this slide. So once I have the electric field vector potential F, I can find the electric field due to this vector F as minus 1 by epsilon curl of F. So let us consider a case of electric vector potential. That means I assume that current density is 0 electric current density is 0, but magnetic current density is non-zero. The source for the field is the magnetic current density, which is non-zero. So how do we find magnetic field intensity? For this case, when J is equal to 0, M is not equal to 0. J is the electric current density, M is the magnetic current density. Yeah, let's use the Maxwell curl equation for doing that. What is Maxwell curl equation? Curl of E is equal to minus M minus J omega mu H. F here shows that this electric field is due to the F vector. Here, magnetic field H is due to the vector F. So now we have curl of E is equal to minus M J omega mu H. So now I know what is the expression for electric field in terms of F vector. Electric field was minus 1 by epsilon curl of F. So I just replace EF by minus 1 by epsilon curl of F. Then take the curl of that. What do I get? Minus 1 by epsilon curl of F minus M equal to minus M minus J omega mu H. So now in that case, if I take this epsilon to the right hand side, I can further simplify it, multiply this epsilon to the right hand side. This is what we are getting. We also have Maxwell curl equation for magnetic fields. Maxwell curl equation for magnetic field is curl of H is equal to J omega epsilon E. So now here if I replace this electric field by minus 1 by epsilon curl of F, this is what I am getting. Curl of H is equal to minus J omega curl of F. So if I combine this term curl in the left hand side and in the right hand side, I can write curl of HF plus J omega F is equal to 0. We also know that curl of a gradient of a magnetic potential, we call this magnetic potential, just like electric potential was phi E, magnetic potential is denoted by phi M. So curl of magnetic gradient of magnetic potential is equal to 0. So in that case, I can express HF plus J omega F is equal to minus del phi M. So I equate these two. HF plus J omega F is equal to minus gradient of phi M. So finally, I have the expression for HF as minus J omega F minus del phi M. So this expression is very similar to we have expression for the electric field due to the vector A. Electric field due to vector A was minus J omega epsilon A minus J omega A minus del of phi E. So here I am finding magnetic field, so I should have minus J omega F minus del phi M. So the relations are very much same. So if I want to find electric field here due to A, then I will write EA is equal to minus J omega A minus del phi E. But now I want to find HF, so I have minus J omega F minus del phi M. So if electric potential F is known to us, how do I find the magnetic field? We have discussed previously, when the electric vector potential F is known, how do I find the electric field? That was minus 1 by epsilon curl of F. So if electric vector potential is known to us, how do I find the magnetic field? Magnetic field can be calculated as minus J omega F minus del of phi M. So once I have electric vector potential, I can find magnetic field also, I can find electric field also. So we can also express the wave equation for the potential, electric vector potential. We have already discussed about the Helmholtz wave equation for the electric field and magnetic fields. But now it's easier to solve the wave equation for the potential. That's why we'll also try to understand wave equation for the electric vector potential. Solving the wave equation is easier for the electric vector potential than directly finding the electric field and magnetic field from the wave equation for electric field and magnetic field. So If I want to get the wave equation for electric vector potential, I can substitute what is H? H is minus j omega f minus del phi m in this curl of f is equal to epsilon m plus j omega mu h. This was what we have derived in the previous slide. If I just substitute instead of HF this expression we have here, what do I get? This is what I am getting. So now finally the wave equation for the electric vector potential would look something like this. Curl of f minus omega square mu epsilon f is equal to epsilon m minus j omega mu epsilon del phi m. Let's say we want to find the fields in the free space where there are no charges. There is no current density. You cannot have current density in free space. So in that case, even the magnetic current density will also be zero. So for that case, source free region, the wave equation will simply become curl of f minus omega square mu epsilon f is equal to minus j omega mu epsilon del phi m. So what's the procedure? Solve the f from the above wave equation for source free region, then find the fields. You can find electric field as minus 1 by epsilon curl of f, or you can find magnetic field as curl of f by j omega mu epsilon. So let us summarize the process. First find the fields, potential, electric vector potential. In order to find the fields, electric field and magnetic field, I just find the electric vector potential F. From the wave equation, we have already derived the wave equation. What was that? Curl of F minus omega square mu epsilon F is equal to minus j omega mu epsilon del phi m. Solve this wave equation and find the F vector. Once I have the F vector, I can find the electric field and magnetic field from this relation. Electric field can be found out from minus 1 by epsilon curl of F. Magnetic field will be found out from curl of F by j omega mu epsilon. So that is the process. Find the electric vector potential and find electric field and magnetic field. As I have already discussed in length that finding the fields are very tough, but finding the vector potentials are easier. So I find the vector potential from this wave equation and find the fields. We can also consider a case of magnetic vector potential. In that case, J will not be 0 but M will be 0. Electric current density is non-zero but magnetic current is density is 0. In that case, we can also do the similar kind of analysis. For that case, wave equation will turn out to be similarly curl of A minus omega square mu epsilon m equal to mu j minus j omega mu epsilon del phi e. This is the electric potential. J is the electric current density. A is the magnetic vector potential. And if we consider source free region, let's say free space, in that case I will not have any current flowing in free space. So this term will be 0. So the wave equation for the source free region will be curl of A minus omega square mu epsilon A is equal to j omega mu epsilon del phi E. So what is the process? Solve A from this wave equation, then find the electric field and magnetic field. Electric field can be found out as curl of A divided by j omega mu epsilon, and magnetic field can be found out as 1 by mu curl of A. So let us summarize it. Solve the magnetic vector potential from the wave equation for source free region, which is curl of A minus omega square mu epsilon A is equal to minus j omega mu epsilon del phi E. Then you solve the electric field and magnetic field from the magnetic vector potential. So electric field can be found out as curl of A divided by j omega mu epsilon, and magnetic field can be found out as 1 by mu curl of A. So now consider case when both electric current density and magnetic current density was existing. So we will have both electric and magnetic vector potential, both F and A will be there. And we also want to consider the case when there is a source free region. Wave propagation in free space is one particular example of that. In that case, the wave equation, when we have both F and A are there, we can solve the wave equation for that, and we can find out the electric field and magnetic field, but we have already considered the case what is the electric field when F vector is existing. We have also considered the case what is the electric field for when A vector is existing. So if we apply the principle of superposition, the total electric field will be contribution from F and contribution from A. So finally electric field will be minus 1 by epsilon curl of F. This is a contribution from the F vector. And electric field contribution from the A vector will be curl of A by j omega mu epsilon. Magnetic field also will have contribution from the F vector and A vector, and we will sum them up by applying the principle of superposition. So H vector will be summation of HF plus HA, and this would be simply curl of F divided by j omega mu epsilon plus 1 by mu curl of A. So now if I want to find the electric vector potential, magnetic vector potential, I solve the wave equation, but I have done it separately. So if I apply the principle of superposition, whatever solution I am getting from two cases, I can sum them up. So finally what we have is electric field will have contribution from the F vector and A vector. Similarly magnetic field will have contribution from the A vector and F vector. So we can sum them up. So this is the procedure for finding the electric field and magnetic field from the F vector and A vector. We'll require this in the following classes. So in this class we discuss about finding the transversal component of the electric field when the longitudinal components of the electric field for the cylindrical waves was the first thing we have discussed. So we have find out the relation between the longitudinal component of the magnetic field and the transversal component of the magnetic field as well as for electric fields. After that we discuss about the vector potential. We have electric vector potential and magnetic vector potential. We have discussed about the electric vector potential, discussed about the magnetic vector potential before, but that was incomplete. We also need to introduce electric vector potential F. So we have discussed about the electric vector potential and magnetic vector potential, how to solve it from the wave equation for source free region. And once we get the electric field and magnetic field from F and A, I can apply principle of superposition and find out the total electric field contribution from F and A vector, magnetic field contribution from F and A vector. So this is the easier approach. Instead of finding electric field and magnetic field directly, you find the electric field contribution from F and A vector, sum them up, magnetic field from the F and A vector and sum them up. This is what we're going to do in the following classes. And once we know this, we can solve the PER and TMR waves for the spherical waves, and that would be the subject of discussion in the next class. Thanks for your attention. Hope to see you in the next class.